Okay, so it's time for us to now go back and prove the first part of the fundamental theorem of calculus. So we're taking as granted the second part of the fundamental theorem, which is we're going to take for granted that the derivative of an accumulation function is equal to the integrand, its own integrand. Okay, so we're going to take that and we're going to use that now to prove this thing, right? This idea that integrating a function lowercase f from a to b can be achieved by just taking the antiderivative capital F and evaluating it at the end and at the beginning and doing a subtraction. So that's what we're trying to prove. Now, in order to do that, here's what I'm going to do. We're going to define an accumulation function of lowercase f. So I'm going to call that g, capital G. And just because I don't want to call it capital F because it might not be the same capital F that that we're working with up there. It's going to be a different function, potentially. So we have the integral, and I'm going to define this starting at 0. Now, it doesn't necessarily have to be 0. It could be anywhere, as long as it's some x, some starting value, some x value that's in the domain of the function, and there's not going to be any like between 0 and x, wherever x is, there's not going to be any discontinuities. Right? So I'm kind of waving my hands and making a bunch of assumptions that 0 is in the domain and it's continuous at 0 and it's continuous everywhere around 0, between 0 and x at least. So yeah, this works really well if you're working with something like a polynomial that's continuous on the entire real numbers. It does run into trouble if you have like a rational function where there's some like vertical asymptote in there somewhere. So let's just assume we don't have a problem like that. We don't have any discontinuities. Okay, so here's my g function defined. Now, what we have already shown with so basically from the fundamental theorem of calculus part 2, we have that g prime of x equals lowercase f of x. Basically, that this accumulation function is an antiderivative of lowercase f, okay? Because its derivative will be lowercase f. That's what the second part of the fundamental theorem said. So now, if this is an antiderivative, right, so g is an antiderivative of f, what we've already shown is that antiderivatives differ from one another only by the addition of a constant, okay? So since capital F is also an antiderivative of lowercase f, we must have capital F of x is equal to g of x plus some constant. And we don't know what that constant is, but it could be anything for some constant c. So, so if this is the case, all right, then what I can do is take my integral, a to b, of f of x dx, and what I'm going to do is I'm going to split this up into two integrals, an integral from 0 to b, f of x dx, minus an integral from 0 to a, f of x dx. And as we've seen, I kind of skipped something here. This could be plus the integral from a to 0, which would be equal to this because the top and bottom limits match each other. But then I've flipped this around so it's from 0 to a. So we have 0 to b and 0 to a. All right, this is justified by those properties. So then each of these is essentially just g of x, but evaluated with some specific x value, right? So this, because it's starting at 0 and going to b, this one is g of b. Now you might say, hang on a second, there's an x inside here, but this one's a t. Well, that doesn't really matter because the name you give to this limit, to this variable of integration is completely independent of the value of this thing. Like you could name that whatever you want as long as it's not the same name as this, right? So it doesn't really matter that this is called x over here because in this case we don't have the x up here, we have the b, and so this could be t. We could swap this out and replace this x with t, and it's exactly the same thing. So don't worry about that. So here, this is essentially the accumulation function with b plugged inside of it. And then over here, this is the accumulation function with a plugged inside of it. All right, just do a little bit of arithmetic here. Let's take this constant function c. Remember this? Let's put the c in there. So g of b plus c, and then minus g of a plus c. If I put parentheses here and here, you can see the plus c I added here and the plus c I added here will actually cancel one another out because of the minus, right? So this has not changed in value at all. I just added c and subtracted c. But now this can be written as f of b. That's because of the relationship between these things as being differing by a constant, and then minus f of a. And we just proved what we wanted to prove. There we go. We did it. Looking back, all we did was we said, hey, there's an accumulation function which is an antiderivative for this lowercase f thing. And if you use that accumulation function and just apply some rules of, some properties of definite integrals, we can write this as a difference in values for the accumulation function. And then we take what we already learned about antiderivatives differing from one another only by the addition of a constant, and just do a little bit of adjusting here with adding and subtracting something, and then we could write it in terms of this other antiderivative, capital F. In fact, no matter what antiderivative you pick, you can just add and subtract the constant and make a small adjustment here to write this as a difference of outputs for any antiderivative, right? I could have added any number c on here that I want, so any antiderivative can be obtained. That's why all you need to do this theorem is just an antiderivative, capital F. Doesn't have to be the simplest one. It can be whatever complicated antiderivative you want. As long as it's an antiderivative, it's gonna work. So there we go. There's the proof of the fundamental theorem part 1. I think that pretty much does it for the section. We've learned how to use this fundamental theorem part 1 to make evaluating definite integrals much easier. We've learned the fundamental theorem part 2, which involves this accumulation function and how to use that like a differentiation rule. And now with these pieces put together in just the right way, we see why derivatives and integrals connect to each other so beautifully and wonderfully. So there we go. This is going to be this idea here is now going to form the foundation for like the rest of calculus for the next several years.